This first statement: on Earth, the ionization energy of an atom of hydrogen, well, actually 6.02 times 10 to the 23rd atoms of hydrogen, right, because our units are per mole, is 1,312 kilojoules per mole. So that means if we're starting in ground state, n equals 1, energy level 1, and we move that electron or remove the electron to n equals infinity, right, infinitely far away from the pole of the nucleus, that would be the energy level change that would represent the ionization energy. On a different planet, we have such a high temperature that essentially all the hydrogen atoms have the electrons in the n equals 3 quantum state. So almost think of the n equals 3 as like the ground state in this case. So the question's saying, what's the ionization energy of atomic hydrogen on that planet? So here we would be doing n equals 3 and then removing the valence electron completely, so n equals infinity. So in this case, the ionization energy is going to be equal to the change in energy of the energy levels. And the equation there is the opposite of Rydberg equation, constant times Planck's constant times speed of light. And then the quantity 1 over final energy level minus 1 over initial energy level. Both of these, are squared. Okay? So instead of actually throwing in all the constants, I've just multiplied them all out together. So we get the opposite of 2.178, that's RHC together, times 10 to the negative 18th. And the units here for all three of these together are joules. All right, and then we're going to sub in our final situation is going to be infinity, okay? And then subtract from that 1 over our initial energy level for this crazy planet is 3. And then we have to square that. So that'd be 1 over 9. Okay, so quick, I guess it's a pre-calc moment that we have to have here. 1 over infinity, 1 over really, 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 really large numbers, that's going to go to 0. And then when you do the rest of the arithmetic, you'll get an answer here of 2.42 times 10 to the negative 19th joules. So that's your change in energy going from n equals 3 to n equals infinity, also known as the ionization energy, also known as the energy of a photon that would be needed to do that job, to remove completely a valence electron starting at the n equals 3 energy level. In doing our dimensional analysis, we're going to say 2.42 times 10 to the negative 19th joule. That's not just over 1, but that's per photon. So that's in every 1 photon who could do this job. Then we can say, okay, well, to get rid of photon here, because we want kilojoules per mole in the end, we can go from photons per mole. We know how many things are in a mole. There are 6.02 times 10 to the 23rd photons in every 1 mole. That's Avogadro's number. Photons cancels. Right now we have joules per mole. Quick fix. There are 1,000 joules in every 1 kilojoule. Now we have kilojoules per mole, which is what we're looking for. So the answer here, 146 kilojoules per mole. And if you compare this value, it's nearly 10 times smaller than this value, but it makes sense because we're starting at n equals 3 instead of n equals 1. So clearly it's going to take less energy to rip off an electron from n equals 3 than it would from ground state at n equals 1.